Welcome to lecture 31. Today we'll be covering another application, membrane theory. And in membrane theory, what we have is this body of material that's it's a 3D plate again, but now it acts very soft. So it can quickly take the shape like if it was a carpet. And here I have the different directions, one, two, and three. So then we have u1 equals 0, u2 equals 0. So there's no in-plane deflections, only out of plane. And it only depends on the location along the 1 and 2 axis. And I should use x1, x2, x3. Let me do that quick. And so we look at the nonlinear strains in this theory. And in this case, we get epsilon 1, 1 equals 1 half u3 comma 1 squared like that. And in this theory, I'll now go ahead and we'll notice that epsilon 3 is 0 in this theory. And I do need the nonlinear terms. If the nonlinear terms do not exist, then epsilon 1 will be 0, epsilon 2 is 0. So this theory is basically allowing for this soft material to be able to bend um, easily. And I could apply a little Q on this as well. So then that becomes very easy. These are the deflection assumptions, the nonlinear strains, and then I start now with the principal virtual work. And you see here, if we assume no body forces at that 0, and the traction here is applied on the top surface here of this carpet or whatever soft material it is. So this is just really Q del U3. And then this right here only becomes sigma 1 1 del epsilon 1 1 plus sigma 2 2 del epsilon 2 2. And clearly now, when I substitute what this is in here, um, I'll get simply um, yes, we get that. And notice how these quantities here do not depend on the thickness. So I'll use the same approach as I used before, which I could use it. Um, and in membrane theory, typically sigma 1 1 will be equal to sigma 2 2 because of symmetry. But assume for a second they're not, is okay. We can go ahead and continue the derivation. So I'll continue here on the right. So I have like that. And this here I'll call the tension 1, tension 2. And when I do that, I get this equal to, and now I'll integrate parts uh, easily. I write this in index notation. I'm going to violate a rule here. You're not supposed to use the index 3 times, so we'll do it now for convenience purposes. And this is equal to the forces applied to the body. So that's integral parts. We have the internal virtual work equals external virtual work. We got this expression here. So we'll go ahead and integrate parts. And so this bottom term goes into the integral. And then we have the boundary term on a closed contour. And then I can use a fundamental lemma and I find that the Euler-Lagrange equation is simply okay. And then we have the boundary condition. This is the Euler-Lagrange equation. And these are here's the boundary conditions. And I forgot the surface normal here. I apologize. Either. So those missing there too. I apologize for that. Or there's no comma alpha. I apologize again. Sorry for the confusion. So this whole thing is wrong. I have to like start over. Oh yes. So we need to multiply this by that by that. So let's do that carefully. And it's really U3 specified. Or So those are the boundary conditions. Either this specified or you have that. And that's the order Lagrange equation here that we got. So yeah, this is how you set up the problem. And if you have the situation, there are situations where it can be shown that T1 is equal to T2 equals a constant. In these situations, then you basically get the Laplacian. Let's call this T. So you can get T. Yeah, so that's how that works. So this concludes membrane theory. So have a good day.